We've been over this before, but again, one, I guess more, crib sheet, okay. I am going to put a criteria on the crib sheet. I mentioned this before, but I noticed a couple people who didn't follow. The crib sheet has to be yours. So you need to write the crib sheet. So don't grab slides or anything like that and miniature them down. The crib sheet should be an exercise on your part in learning in some sense, and just grabbing and pasting slides is not an exercise. Plus you're violating copyright and I can sue you. Well, they're not mine, but someone can sue you. But yes, make your own crib sheet. So you can type it up, I don't care how you get ink on the paper, but it should be yours. And you can do your own. And there's value in both old crib sheets. So I suspect your Unit 2 crib sheet has some of the S stuff on it, transfer functions and whatnot. So you can reproduce that again, I'm sure. The Unit 1 crib sheet, all the node analysis and mesh analysis, which we did now with phasers. Yeah.
Is this examining any of the loss transformations?
No. Other than you should know what the impedances are. So you should know ZC is 1 over SC, ZR is R, and ZL is SL. So, but no, you don't need to do any of the table stuff. You will need that in the final, of course. We'll revisit that one. If that's it. Any other questions on the exam? I think we're over in Ricketts again. If it warms up nicely over the weekend, then we should have a nice miserable Monday evening. Try to bring a fan. Any questions on anything? Got any questions? I know people were asking me if they had questions on the homework. I don't remember what number 4 was. So we had a table that was just presented in a table for some arbitrary reason. So what is this? Well, if we plot it out, it looks something like this. There's a pass band, 10 to the 3. We have a minus 6 dB correction. We write minus 6 dB correction relative to the pass band, which we should recognize, which is equivalent to 4 dB. You see that in the table. And we have 40 dB roll-up. 40 dB roll-up. So what did we build here? What type of circuit is that? It's a high-pass filter. At 10 to the 3, what do we have? Well, we go from plus 40 dB per decade as a slope to 0 dB. So what does that mean? At 10 to the 3, effectively, what do we have to have? So this is a double pole. And in this particular case, is this a real pole or a complex pole? And when I say a complex pole, I'm really talking about resonant frequency as opposed to poles, as opposed to real numbered poles. So resonant frequency is a real number when we have an underdamped circuit, rather than talk about the poles directly, which are complex. we talk about the resonant frequency, and I want to bring this up again because I've had a bunch of people ask me. If the circuit is underdamped, there are still 2 poles in it. They're complex. So rather than look for complex points on a real curve, we look at the resonant frequency and consider that our double pole. And that comes back to what we had said previously when we were sketching these things. In the underdamped case, we start with the critically damped straight line approximation. The critically damped curve with its -6 dB point, if it's a high pass filter or low pass filter, or band pass for that matter. We start there, we use those asymptotes, but we use omega naught as if it was a pole. No, it's not really a pole, but it is a point, a frequency at which we have the information and we can use that. So in this case, is this a real pole, real double pole, or a complex conjugate pair of poles? Well, how do we know? How do we know? I mean, I just said it a second ago. How do we know whether that's a real double pole or a complex conjugate pair? A couple people said things, but they didn't quite hear. So how do we know? Someone then, yeah. The correction. The correction tells us everything. What's our correction relative to the passband? -6 dB. What does that correspond to? There's only one thing. If this is a double pole and it's -6 dB, what does that mean? It's critically damped. If it's a second order circuit. But if it's critically damped, are the poles real or complex? They're both real. We have a double real pole. If we're talking about real poles, can we build this circuit with first order filters, first order stages? Yeah. Can we build it with a second order stage? Sure. So if you're talking about real poles, and you have 2 of them, you need 2 of course, you can build this with an RLC second order circuit, or you can build it with cascaded first order stage. What does our transfer function look like? This is a high pass filter. We can build it as 2 high pass filters cascaded. So we can do first order, first order. And we can do RC, RL. We don't do RL very often, or I don't. I know some of you have. We've got voltage follower in there. Some grounds. Be out. Be in. And just to emphasize, it's be in as a source. I don't know, we can pick some numbers here. 0.01, 0.1, it gives us reasonable resistance, 0.1. So very quickly we did this as 2 first order stages. Another, yeah. Yes. Since it's a high pass. Thanks. -1 for me. Good. That's what I get for going out of my normal. So, alternatively, we could write this as S squared. S squared plus 2 times 10 to the 3, S plus 10 to the 6, right? Those are the same thing. And if we treat this as a second order RLC circuit, here's alpha, here's omega naught squared. Omega naught squared equals 10 to the 6, which equals 1 over LC. And alpha, this is an RLC series circuit. 2 alpha equals 2 times 10 to the 3 which is R over L. And so we can build this using RLC circuits. Pick a value again. We can use L equals 0.1, use the same thing. 10 to the minus 5. And that gives us an R again equals 100. And what are we looking at now? Again, there's our Vn, R, C, and L. Do we agree? Is anybody not sure? Say something. Questions are the thing to ask. I couldn't hear. Is nap time? I couldn't hear. Here. Oh yeah, here. Which is what I usually do. So yeah, our cap would have looked, and then I would have been. Sure. In a large sense, though, which component are you more likely to see used? Yeah, capacitors. Inductors are more problematic, typically. So more often, you would build this with a capacitor. Yeah?
Do we have to consider the fact that it blasts out at 10 dB?
Oh yeah, I left off my gain. You're right. So I need an amplifier here. Right. So this I need about 3 times gain. So something like that. There was a 10 dB. I think it's something like that. And then you need an amplifier here too. Well, I was just looking at the filter part of the circuit, but yeah, there was a plus 10 dB, so there was a K in there, right? So, yeah. What's that?
So I can just throw an op-amp in there just to make it 10.
Sure. This is the only way to get gain is to have an op-amp. So I see a couple questions, I'll come in. The only way for the pass band to be larger than 0 is to have an active component. I mean, that's worth writing down. If the pass band, the flat portion, has a value, and here I should put a little approximate value. Maybe I'll just write it out. An approximate value, because it's not truly flat. Greater than 0 dB. Okay, you guys playing phone tag with each other? You must have an active component. In other words, an op-amp. An op-amp is an active component. It has its own power. Passive components, resistors, inductors, capacitors, they don't produce any power magically. An op-amp does produce magic power. Not quite magic, but we must have an active component. So if we have, in this case, as was a true problem, if this is our 0 dB, and this is at 10 dB, there must be a K. Must be an op-amp. With gain K. In this case, 20 log K equals 10 dB. So there has to be a gain state, there has to be an op amp. You can't, I mean, the RLC circuit, we've seen the RLC circuit under damped at the resonant frequency goes above 0 dB, sure. But we're not gaining any power there, and that's not really contributing to the pass band, so to speak. That's creating this, you know, bump up here, which isn't doing anything for us in terms of gaining power. You know, this 10 dB, this is an increase in voltage, but it's also an increase in power. So whatever our active component is, it's suppressing power in the world voltage. Yeah.
But I know on the previous homeworks, like you had your matrices with imaginary numbers.
Oh, am I going to do that on the test? No matrices with imaginary numbers on the test. Unless you really do something in a crazy way. So none of the problems will be designed to solve matrices with complex numbers. So. I did that once, and it was a 2 by 2 matrix, and even that wound up in the mass, and I won't do that again. I mean, if you choose a certain way to solve the problem, you can wind up with a matrix, but it's not the way I had it in my mind. So if you get a matrix, you're doing something the hard way. So, yeah.
You have to worry about like the double zero at zero, like you need to put in an exponent.
Right, and I should have brought that up last class because a couple people asked me that during the team assignment. You don't. I mean, the double zero at zero is an artifact of where you're measuring things. So if we look, you know, at our high pass filter, in this case, plus minus B out. I mean, what's H of S, B out over D in equals SL over SL plus R, right? R and L. And we could rewrite that as S plus R over L. The 0 at 0 is an artifact of where you're measuring in the circuit. Now certainly this pole is part of the design. So you design for the poles, but the fact that there's a 0 at 0, that's an artifact of the circuit. And so even here, like we had talked about this before, worth knowing. In our RLC circuit, if we measure V out across both L and C, well, H of S in this case is S squared plus omega naught squared, S squared plus 2 alpha S plus omega naught squared. That's what the transfer function is. There's a 0 now, a double 0 at omega naught squared, right? Effectively. And so, do we worry about designing for this? No, it's an artifact of the measurement. You design for the two poles that are in the denominator here. Now, that's not saying you can have more complicated circuits where you can design for the zeros. And you do. So, it's not out of the question, but in our simple circuits, they're an artifact. But you would never design for a 0 at 0. It's not a circuit design, it's an artifact of where you're measuring the measurement. In this case, you design for the poles and the 0 falls out somewhat automatically, even though the 0 is meaningful. What was this circuit again? Anybody remember? Depending on the band stop. We looked at this. How can we tell that? And we can do this by inspection. How do we do this? What are the 3 points we look at for the second order transfer functions? We get a transfer function in order to characterize the transfer function, what do we look at? We've done this a bunch of times. What do we look at in order to find out what kind of filter it is? You look at S, as S approaches 0, what else do you look at? Infinity. And then, well, the damping ratio tells you whether it's underdamped, overdamped, or critically damped, but at the resonant frequency. So those are the three things of interest. Now you look at H of S goes to 0, as S goes to 0. H of S as S goes to infinity, and H of J omega naught. And there's, 4 cases here we can look at, 4 meaningful cases. We can get more silly than that, but 4 meaningful cases where this goes to 0, this goes to 1, there's your high pass filter. This goes to 1, this goes to 0, there's your low pass filter. These both go to 0, this goes to some finite value, there's your band pass filter, and then the flip side, this goes to 1, this goes to 1, this goes to 0, there's your band stop filter, which we just saw in that previous slide. That was quick. Does everybody follow what I just said? Any questions on that? I mean, these are things worth going. These are concept type questions you can see on the
To
exam.
go over the other pairs of components, like if you take voltage over RL and RNC.
And that's where it gets a little bit silly when you could. And so that gets a little bit less meaningful in terms of a design, but sure, let's look at it for a second. Actually, I'm not sure I can do it quickly off the top of my head, but let's see what happens. See how many mistakes I made. Let's call this V out. And so it's worth an exercise just going through the algebra here. We haven't done it for a while, so H of S, again, V out of S over V in of S. And if we do this in terms of impedances, this is ZR plus ZL over ZR plus ZL plus ZC. I mean, so that's a straight up voltage divider. Everybody agrees? We haven't used that term for 5 minutes, so it's worth saying again. And so impedances in series add the total impedance. And now we can plug in R plus SL, R plus SL, plus 1 over SC, and a little bit of rearranging here. S squared LC plus SRC, squeezing this in, S squared LC plus SRC plus 1. And then one final step of algebra, S squared plus R over LS, which is 2 alpha, and then S squared plus R over LS plus 1 over LC. So effectively we wind up with S squared plus 2 alpha S, S squared plus 2 alpha S, plus 1, plus omega naught. So what does this look like? Well, depends on what these values are, but we can make some observational comments. How many poles do we have? We have 2, whether they're real or double or whatever. Depends on the damping, of course. What can we say about the zeros? We know 1 0 is at 0, right? And we can factor this out. This is equivalent to S plus S times S plus R over L. So there's a 0 at 0 and another one at 2 alpha. Do we agree? And so what does this look like? Well, it depends what alpha and omega naught are. But there's a 0 at 0, so, and then we would perhaps cross a pole, maybe it does something like that. Now there's going to be Yeah, I think actually it's gonna, something like this maybe. Flatten out, step up. Again, it depends a little bit on the values. And so, I mean, it's not a bad question, but it's not something we would deliberately design. So the band stop, the high pass, it's not a bad test question, but not a particularly useful circuit. I don't know. I don't know everything about every possible circuit design. Maybe there's an application here. None that I know of. I think that's right. Any other questions? Must be more questions.
Yes, what about the problem file? Homework problem file.
Homework problem 5. Let's do it. Let's try that. Use it. But you already handed in your ones. So this was a low pass filter. Omega C was 100K. That wasn't omega C. FC equals 100 kilohertz. Pass band. It's around 2 dB, plus 2 dB. So 2 dB over 0. Would you ever make a pass band with negative dB? I can't think of a good reason. Effectively, what are you doing? You're attenuating every signal on a pass band. It's usually not something you want to do. Usually those are the signals of interest. Again, maybe a test problem, but roll off 80 dB and at FC a minus 6 dB point relative to the pass band. So, what can we say about this circuit? We go from a flat pass band to 80 dB roll off. Effectively, how many poles do we have? About 4, or precisely 4. We have 4 poles. We go from 0 dB to 80 dB roll off. So we have 4 poles. It's actually not so many. Again, better filters are higher order, so this second order stuff is, not, this is weak. Higher order filters, much better roll off, other pass bands, or less variation in that effect. So we have 4 poles. If we have a quadruple pole, relative to our normal straight line approximation, what would be the correction at the cutoff frequency of the pass band? Minus 12. So normally we would have minus 12 dB if all our poles are real. If all real, minus 12 dB at FC relative to the pass band. And then minus 10 dB. Well, minus 12 dB, that's not spec. Spec was minus 6 dB relative to the pass band. What does that mean for us? We must have an underdamped circuit. Do we have to have 2 underdamped circuits? No. So we can have 1 underdamped circuit with what correction? 0 dB. Relative to itself. So relative to its own pass band, it would contribute 0 dB at the cutoff frequency. which is 2 pi times 100,000. What could the rest of the circuit be? Could be first order. So this is a low pass filter. We could do something like this. And call this R1, C1. And call that R1, C1, make them both the same. Well, 1 over R1, C1 equals 2 pi times 10 to the 5. Everyone agree with that? That was our cutoff frequency. That was part of our spec. Since we did get F here instead of omega, we need to multiply by 2 pi. And so these are two real poles. So this guy contributes to minus 3 dB, minus 3 dB at FC. FC. This is at FC colon. It's a little bit more fancy. So what are we left with? Well, we need an RLC circuit. And again, measuring across the cap, since it's a low pass filter. And then we also need some sort of gain. I could have put it here. I don't have to put it at the end. Yeah. Here, this gives us 20 log K equals 2, approximately 2. Where K, call that R4, call that R3. K equals R4 over R3 plus 1. And then we have some R2, C2, and L2 for consistency. What do we know? This is an RLC series circuit, omega naught squared equals 1 over L2 C2. Yeah.
Is the C supposed to be where the L is and the L is?
Yeah. I mean the labels. Well, you can call them whatever you want. They're just names, but meaningful names are better. So the circuit's correct, but the labels were stupid. But anyway, omega naught squared equals 1 over L2 C2, which is, don't have much room in there, 2 pi times 10 to the 5 squared. And then 2 alpha is what? What does alpha have to be? Well, we said, what does our damping ratio have to be? We said that earlier. Damping ratio has to be 1/2, which means alpha equals omega naught over 2. And that winds up being 1 over 2, R2 over L2. I didn't plug in numbers there because I don't feel like doing the 2 pi in my head. I messed that up, certainly. Does everybody agree with what we did? Is there still a question, or does it make sense? What else could we have done? Like I said, we could have taken this, lumped it in here. What could we have done here? We could have made this a second order circuit with what damping? We would have done it critically damped if we kept this the same. Alternatively, could we have done 2 underdamped circuits?
Yeah.
Sure, we could have done an underdamped circuit that both have minus 3 dB relative to the pass band. Just a second. If it was minus 3 dB, what's our damping ratio? This is one we want to be familiar with as well. 1 over square root of 2. Right.
Why couldn't you use an overdamped circuit?
No, you could. Oh, here? Well, if this has a damping ratio of 1/2, and if you replace this with an underdamped circuit as well, then our correction is going to be above minus 6 dB. So if we replace this with a critically damped circuit, that's going to contribute minus 6 dB at our cutoff frequency, right? This already contributes 0 dB. So that meets spec. And so if we replace this with something underdamped here, that's greater than minus 6 dB or less, I guess less negative.
How would that go overdamped? Could you use an overdamped?
If you do an overdamp, then you're going to actually move down. So if you think about, here's just our critically damped case. This is a minus 6 dB. If we overdamp with the same resonant frequency, same omega naught for both, then we wind up with something that looks like this. And this is lower than minus 6 dB. So this is minus 6 dB, this is less than minus 6 dB. And the more underdamping you do, the smaller it gets. The more overdamping you do, the lower it gets. Does that make sense? This is still omega naught in both cases. On dB scale, where is this point relative to the two poles? It's halfway in between. It's the square root of the square, or square root of the multiplied, which is halfway in between on dB scale. So if you think about it, as you spread this out, this point's moving down. You know, you keep doing this. This stays the same, the asymptote here stays the same, and you introduce this 20 dB slope that's pushing that point down. But maintaining same omega naught square, that's important. Any other questions? Yeah.
Does the underdamped stage include a double pole? That
Always.
always?
I mean, it's a double pole. So no matter what, H of S, we don't even care what's in the numerator, but we can use our low pass. How many poles are in the denominator here? No matter what. Doesn't matter what the damping is. There are 2 poles in there. So as S goes to 0, this is a slope of constant slope, horizontal, 0 dB. As S goes to infinity, our slope is minus 40 dB. Somewhere in between 0 and infinity, we cross 2 poles. We don't have a choice. There's 2 roots in this Pythagorean solution.
But in order for it to be a double pole, don't have to be the same root.
Well, that's, again, when we talk about underdamped is complex poles. So, I mean, here, write it out, overdamped. 2 real separate poles. And I can never remember how to spell separate, so this is what spell check's for. Critically damped. That's one of my bad words. 2, a double real pole. So these, no problem. We look at these, overdamped minus 3 dB at that pole relative to the straight line approximation, double pole minus 6 dB. Underdamped, still 2 poles. Nothing's changed. 2 complex conjugate poles. Conjugates. But instead of looking at the poles, we now consider omega naught squared, or omega naught instead, for our Bode plots. We need to consider something that's real. So we consider omega naught instead. Why? Well, this is a double real pole. Where is it? Which is omega naught. That's omega naught. So that's our starting point. We said this before. Again, the underdamped starting point is with the critically damped case, with the kind of goofiness of the bandpass filter being an exception. There we look at the inverted V. But for the high pass filter and the low pass filter, the starting point for the underdamped case is the critically damped case. And we still consider omega naught, which is the double real pole for the critically damped case. So there are always two complex poles, no matter what. Between S go to 0 and S go to infinity, there are two poles. Somewhere in there. So we have, between those two limits, we have to have a change of minus 40 dB in the slope, no matter what. And we see that in every filter. So. Even the stupid filters, you see that. This is important, so is it clear? Any other questions?
Does this problem be solved by two cascading second order average circuit with each with minus 3 dB?
Yes, sure. Or minus 2 and minus 4. I mean, the advantage of minus 3 is they're both the same. And that's always, I mean, less work is always better.
I have a question about for the first order circuits, when you have some like a rule, like based on pole, it has like minus 3 dB thing, and
Right.
also have the zeros, it have like plus 3 dB.
But the first order circuit's never going to have a 0 other than have 0.
But after we just like have second order, we that works.
So, I mean, if we go back to the question that was brought up earlier, where we looked at this guy, we measured across the resistor and the inductor. Then, yeah, so this is a real 0, or, well, it is a real 0. We have 0 at 0 and a 0 at 2 alpha. And then here we have, I don't know, P1, P2, depends what the damping is. So here, when we cross this 0, so looking at the Bode plot that I kind of scribbled on a little bit, we would have a minus 3 dB correction there, a plus 3 dB correction there, and then a minus 3 dB correction there. Those aren't absolute values, those are relative to the location of the straight line approximation. Was that your question?
No, I mean, I think so.
Do you think that was, well, that was your question, so, you sure?
But
I mean, you sure I answered what you were asking?
but it's like for
The
the
second
first,
is right.
for the first order, we have something like where we have like say it's a high dB, like HP thing.
High pass filter.
Yeah, high pass filter. And it has like if it has like two poles and a 1 dB.
But it's, I mean, if it has 2 poles, it's not first
Oh, and
order.
one pole and the 1 zero is a 0 dB for correction, right?
I mean,
Sounds like that.
I mean, do you have something you're looking at?
I think what is being asked is that when we have the double poles in the second order undamped case, do we still factor in the -6 dB for the double pole?
No, that's why you look at the resonant frequency, but, I mean, you have something squared here.
But like what you, this is what you for the, first order circuit?
What you have written, just to make sure I'm understanding, is you have,
No, the real, like, the words I write, like it's unfold,
N pole has a minus 3 dB correction at the pole,
yeah.
and the N zero has a plus 3 dB correction at the zero.
There's like, for the first order, like it's S over, say it's S over like, a number plus S, something like that, and it's supposed to be 0 dB, but usually it's like for, at each first order thing, it have a minus 3 dB correction.
So every pole.
Like, yeah.
Every pole has a minus 3 dB correction.
Oh,
Every real pole. When we underdamp, then we don't look at that anymore, we look at the damping ratio. So real poles have minus 3 dB correction. Underdamped depends on the 2 delta, the two times the damping ratio. So again, to go back to what we just looked at, an overdamped low-pass filter. It looks like this. This is 20 dB roll-off, 40 dB roll-off. There's a real pole P1, there's a real pole P2. This is 0 dB here. This is a minus 3 dB correction. This is a minus 3 dB correction, right? Critically damped. Low pass filter, same thing. This is 40 dB roll off. This is P1, which equals omega naught, so that's a double. And this is a minus 6 dB correction relative to the pass band. Underdamped is different because we don't have real poles anymore. We have 0 dB, but we start with this equivalent. And I should draw a dash line, reaching the asymptote as you get far away. This point here, whatever it is, that's 20 log 1/2 times the damping ratio, which can be more than 0, which is greater than or equal to minus 6 dB, or greater than minus 6 dB. So that's minus 6 dB or higher. When does it go larger than 0 dB? When the damping ratio is less than 1/2. Did I get your question? Sure? Okay. Is that clear? So only at real poles do we have these automatic corrections. At the underdamped case, we need to look at this map. Yeah.
So for underdamped and pass filters, is a different equation?
Underdamped bandpass, it's the same expression, but here's our 0 dB line. At omega naught is a 0 dB. This is the bandpass filter. Omega naught is always 0 dB. We can now look at the inverted V. This is 20 dB roll off. That's 20 dB roll off. This is second order. Certainly we can achieve better with higher order, the second order. 20 dB roll off, 20 dB roll off. There's our vertex. This distance here, 20 log 2 times the damping ratio, is the position of the vertex. No, let's make it inverted. So that's the position of the vertex of the V. And again, it can be greater than 0 dB if we're at critically damped. It's at plus 6 dB. If we're at a damping ratio equals to 1/2, it's actually at 0 dB. And as that damping ratio gets smaller, as you underdamp more and more, it moves down. So in our little plot here, this would be strongly underdamped. And you could sketch it out, something like that. Did that answer your question? Yeah.
So once again, is that that 20 log 2,
Times the damping ratio.
is that the distance of that line from the vertex to 0 dB?
Yes.
There's really works for BPL.
Well, we had the same, yeah, just to, I guess, point out the logarithms. These are the same. What's the difference between these two? One's negative. So this gives you the position of the vertex relative to 0 dB. But magnitude-wise, these are the same values. So in both cases, I'm giving you the position. Yeah.
Right, so for this case, you still start with the critically damped case, and you shift the whole thing down.
So, yeah.
And then,
So the inverted V is effectively a critically damped case.
and then shift it down and you reach up to 0.
Right. Yeah. The bandpass filter all have this V, even the overdamped case, but the overdamped case hits the 0 dB and then flattens out. So even the overdamped bandpass filter, which some of you I know designed in the homework, I mean, here's our 0 dB, overdamped, DPF, second order. So these are both 20 dB roll-off. Nothing's changed here. Where's our inverted V? Well, it's way up here. So it still exists. It's just truncated. We just truncated everything that was above 0 dB. And this follows the same rule. This distance winds up being 20 log of 2 times the damping ratio. So that's still valid. I mean, if you wanted to do it this way, you could. Does this make sense? This is a positive number. What can we say about the damping ratio? What can we say about the damping ratio when it's overdamped? It's larger than 1. Is the 20 log 2 times something larger than 1 going to be positive? Yeah. The vertex is going to be way up there. So, yeah.
So, in that case, when delta equals to 1, the vertex
We mumbled a little bit at the end, but the vertex is going to be at 6 dB. So in the critically damped case, and we did that last week, so it should be in your notes somewhere, but in the critically damped case, where's the vertex of the V? At 6 dB. Why? If it's critically damped, what's the correction of the straight line approximation? Minus 6 dB. Well, it's minus 6 dB relative to the straight line approximation. But where is the resonant frequency always in the bandpass filter? At 0, without any gain. If there's a K in here, if there's an amplifier, of course, everything shifts up. But just by itself, if we're looking at the bandpass filter, omega naught is at 0, but because it's critically damped, that would be minus 6 dB relative to the straight line approximation. So that means our vertex is at 6 dB. So to draw that out, essentially we would have this. There's our critically damped. And that distance is 6 dB, and our real point is right there. Does that make sense? Everybody okay with this? I have found in my experience the bandpass filter is the most confusing. Low pass filter, high pass filter, a little bit more straightforward.
Can you go back to the low pass filter? Yeah, on the next yeah.
This thing?
Yeah, is so the ratio, the 1/2 delta, and for everything else it's just 2 delta.
Well, this would be underdamped low pass filter and also a high pass filter.
I'm just curious about what's inside the log, 1/2 delta, because in the other cases it's just 2 delta.
But they're the same, they're effectively the same thing. It's just one is the negative of the other. So here, I mean, all I've done is I've taken out a little bit of mathematical steps. This is the position of the Bode plot at omega naught for the high pass filter and the low pass filter. In this case, this is the position of the vertex. So we're looking at two different things here. This is the position of the correction to the Bode plot. This is the correction to the vertex. So in some sense, if we write it out a little bit mathematically, I mean, we could write it as straight line minus actual. Right? I mean, essentially, that's kind of what we're doing with minus 3 dB points. Straight line approximation versus the actual point. If this is a real pole, this goes to minus 3 dB. That's what I gave you here. Here, I gave you the reverse of that. So if I take the negative of this, then I take the negative of that, you get this. Does that answer your question?
Yep, that's exactly it.
Is everybody clear on this? And they're effectively the same thing, it's just which one I'm using as relative. So A relative to B is the negative of B relative to A. You can look at it from either side, it doesn't matter. And if I take the negative, well, the negative of the log is just the inverse. 20 log 1 over x is minus 20 log of x. So I'm not trying to do anything tricky here. I'm just trying to give you the relative position of two different things. Here I'm giving you the position of the actual correction. Here I'm giving you the position of this vertex, the straight line approximation. Yeah?
Is there any rule of thumb for drawing the underdamped case where it's for the manifest filter, like for the actual curvature, or would it will anything?
You mean how to draw this, how wide is it? Yeah. Maybe there is, I don't know. I mean, nothing that I've really looked into. I mean, it does get stretched out. I mean, if you strongly underdamp this, I mean, relatively, you know, it gets tighter at the top. Narrower. So yeah, where does it get the straight line approximation? Yeah, maybe a decade out. I haven't really thought about it, so I don't want to say something that's totally bogus, but I'm not sure it's really something that's critical. I mean, it's a little bit like the phase plots for the underdamped case. I mean, there's no real, it's not something that people really get concerned about. So more questions? No more questions? All right. Let's take a minute. There was something I actually wanted to go over a little bit today, and I wanted to glance at the test as well. So go get a drink, whatever. Meet again in a couple minutes. Do you pause it during breaks? Come up with over there. Brief recess. Nobody has any more questions on anything? Okay. I did want to visit something you talked about a little while ago and just go through some of the reasons for things. So, low pass filter, 2 first order stages. This is not critical here other than the concept, so you don't gotta burn yourself out taking notes. I'm gonna just do it and show it to you. So we could have something like this. We've built this a number of times before. Nice voltage follower, though we put an amplifier in there as well. Yeah. R1, C1, R2, C2. And we should recognize H of S equals 1 over R1, C1, 1 over R2, C2, S squared, let's just do this a second, please. 1 over R1, C1, S plus 1 over R2, C2. And it should be clear that these are both, first order low pass filters. 2 real poles. Effectively, it's going to be overdamped or critically damped, depending on what those poles are, if we use second order concepts. Apparently, I was very excited. Now, this voltage follower I've always contended is important. So we can look at the case R1 equals R2 and C1 equals C2. Effectively, what do we have? We have a double pole. What's wrong? That's an S screw. An S to the 1. So if we choose both of those to be the same, we have an R1 and an R2, or R1 equals R2, C1 equals C2. We have a double pole at whatever that frequency is, 10 to the 6 or something like that, 10 to the 3. And we can even pick values. Let's say 1K, 10 to the minus 6 equals 10 to the 3 radians per second. Well, where I'm going with this is I've contended that that voltage follower is important. We've never actually went and looked and checked. And so, if I didn't have that voltage follower, well, what does our circuit look like then? And this is a circuit we've actually seen before. You had to do this at some point. And this is a lot more fun mathematically. And a little bit of algebra in there. We could write out H of S, in this case, is going to be ZC2 over ZC2 plus ZR2. Again, this is not vital that you write everything down here. ZC2 plus ZR2 parallel with ZC1 all over ZC2 plus ZR2 and parallel with ZC1 plus ZR1. I did that a little bit quickly, but does everybody kind of agree with what I wrote down? We have 2 voltage dividers effectively there. We have the voltage divider giving us the voltage at this point, and based on that, the voltage at this point using the voltage divider. And we had to do a very similar problem back in Unit 2, maybe even with homework 7, I don't remember. And with just maybe 2 or 3 hours of math, we wind up with something along the lines of, it took me about 5 minutes, so S squared plus S, 1 over R1 C1, plus 1 over R2 C2, plus 1 over R2 C1, plus 1 over R1 R2 C1 C2. And effectively, this is our 2 alpha, and that's our omega naught squared. If we think about this, here's the transfer function without the voltage follower, and here's the transfer function with the voltage follower. Not so dissimilar. The numerator is certainly the same. And we multiply our 1 over R1 R2 C2, we get an S squared in the denominator. The omega naught squared is going to wind up being the same. But this middle term, a little bit different. I should have written this out, but we can write this as 1 over R1 C1, or R2 C1 C2, S squared plus S 1 over R1 C1 plus R2 C2 plus 1 over R1 R2 C1 C2. Very, very similar transfer functions. Does that voltage follower matter? And the answer, and I brought this up before, is maybe. When does it matter? Well, we look at these terms. This guy's the same, this guy's the same, these guys are the same. The S term almost the same. 2 of the terms are here. We have this additional term, 1 R2 C1. Does that matter? Well, if we go back to this example up here, we wind up having, this is a double pole at 10 to the 3. For the same example, R1 equals R2 equals 10 to the 3, sorry, 1K. C1 equals C2 equals 10 to the minus 6. In this case, what do we wind up having? Well, there's the pole 1 at around 300.
You bump it up.
And I don't remember where the pole 2 was, somewhere around 5 or 4 times 10 to the 3. Is that an impact? Are they different responses? Yeah, I would say that's pretty significant. So we have a pole at 300 radians per second as opposed to a double pole at 10 to the 3, much, much lower. The pole is, much, we have a much smaller pass band, one way of looking at it. That's fairly significant. On the other hand, what about if we have a very different situation? For example, if we have omega C1 equals 10 to the 3, and omega C2 equals 10 to the 6, which of course is a stupid filter. I mean, that's gradual roll-off, pass band up to 10 to the 3, 20 dB from 10 to the 3, 10 to the 6, and then 40 dB after that. If we did that same design, arguably, what type of response would we get here? Well, actually, they'd be pretty close to the same. So if our values are sufficiently different, and there's some ratios here that matter as well, if our poles are sufficiently removed, that voltage follower is not really necessary. When we have poles and zeros clustered up very close to each other, we need that isolation between each circuit. And as I mentioned, real filters, they have more poles and zeros. You'll see that, those of you who take signals, you'll see that in the design of Butterworth filters and Chebyshev filters. much more poles than zeros, and you need that isolation in stages, or it can be very useful. There are other ways of doing things, of course, as well, but to achieve our goal here, in this, if the poles are close together, you have to have the isolation. If the poles are far apart, you can get away with things. And you can see it all comes back to this term. If this term is insignificant relative to these two, then these circuits are equivalent. And that's kind of the moral of the story. There are other things you could look at in the book worth looking at. There's the sound and key filters. Nice discussion. There's some slides about that as well in one of our, I don't remember which slide, one over the past couple weeks. There's some pictures of those. A little bit more complicated design, but they use capacitors and resistors only to get second order effects. So more practical in some sense. Again, we usually try to get away from using inductors. So there are other circuit options, though the math gets a little bit more complicated. All right, so let's take a glance at the exam, last question's exam, look at some of the questions. Again, classic layout, nice short questions. Some of these we just talked about. In the second order RLC series, circuit with only passive components, no amplifiers. Can you have, is at the resonant frequency, is that always a 0 dB point? So RLC circuit, series circuit, or parallel for that matter, doesn't matter. Resonant frequency is a 0 dB point, yes or no? No. Resonant frequency is located at 20 log 1/2 times the damping ratio. Also for high pass filter. And what about choice B, band pass configuration? We've already spent like 20 minutes on this, so everybody better get that right. Yes, the resonant frequency for the band pass filter is a 0 dB point. So we have false, true, false there. I think we've seen that a bit. So if you look at question 2, maybe a little bit more back in time for us. We haven't done this for a week or so. So as S goes to 0, the voltage across resistor 1 goes to what? V source. Everybody agree with that?
Yes.
Why? Why? The inductor shorts. If the inductor shorts, what's the voltage across R2 and C? 0. They're comparable to short, so no current's going through there. And so if that's a short, then all the voltages across R1. As S goes to 0, then the R2 is 0. We just said that. What about as S goes to infinity? What's the voltage across R1? Why? Capacitor shorts, the inductor opens, and as was said, you get a voltage divider. In R2, the R2 then, the other voltage divider, R2 over R1 plus R2. Everyone agree? Anyone not sure? It is a frequently missed question. Variations on that. For an RLC parallel circuit, increasing the resistance will increase the equivalent total admittance. So admittance is the inverse of resistance. If you increase resistance, what happens to the admittance of the resistor? It decreases, and the admittance in a parallel circuit, Y equivalent equals what? The admittance of the resistor plus the admittance of the capacitor plus the admittance of the inductor. In a parallel circuit, admittances add, and so if you decrease one admittance, the overall admittance decreases as well. Right? Everyone agree with that? We didn't write that down, we can. Anybody not sure what I just said?
So if you get the feminine impedance have to take the admittance of each individual component and the special.
Well, the Thevenin impedance not really related to the admittance.
Like just if you
Just trying to think that through for a second.
like if you have the total resistance or
The total impedance.
impedance across some circuitry, is the inverse of that numeric the admittance, or do you?
Yeah, sure. So, yeah, absolutely. So if, I mean, this is the parallel RLC, but if we look at something a little bit more complicated, we can call it, let's draw something else in there. We could redraw this. There's a lot of yawning today. You partied hard last night?
Circuits part.
Circuits party. We could call this Z1 and Z2. Where Z1 is R1, Z2 is ZL plus ZC in parallel with ZR2. And so, yeah, the admittance of this Y2 is just 1 over Z2. Which, if we do this as inverses, we could just write somewhat quickly as ZR2 plus ZL plus ZC over ZR2 times ZL plus ZC. I did that quickly, but does that make sense? So yeah, any chunk, you can break down any chunk. And if we know the voltage across this, I mean, we can take this one step further, which makes it an interesting potential test question. Call this V2, I2. This equals I2 over V2. In complex form, phasor form. So that would have to be complex. Or S's. Makes for a potential test question.
No, not yet.
Part of it. I wrote the easy problems. I got it down to about 16 pages. For an RLC circuit, increasing the resistance will increase series circuits will increase the damping ratio or decrease the damping ratio. It increases the damping ratio. The larger the resistor in an RLC series circuit, the larger the damping, the more attenuation in some system. What about in the parallel RLC circuit? Not true. Increasing the resistance does what to the damping ratio? It decreases it. I mean, we can prove it mathematically. With some I source. In this particular case, omega naught squared is still 1 over LC. 2 alpha, though, is 1 over RC. And so, or alpha. So the damping ratio, alpha over omega naught, equals 1 over 2 RC. When we invert this, square root of LC. That's proving it mathematically, but thinking about this physically for a moment. What does damping mean? I mean, what does damping mean? In some sense, I mean, if we consider increasing the resistance in a simple RC circuit, what effect did that have in terms of charging? Less current, which means it takes longer to charge, right? So if we have an RC circuit, we increase the resistance, it takes longer for the capacitor to charge. Well, if we throw an inductor in there, we get an RLC series circuit. If the resistance is high, do we think it's going to take a long time for things to change? Yeah. Well, effectively here, if we increase resistance, what are we doing? Well, this is a current source. That current's got to go somewhere. If we increase resistance, arguably, I don't know why that was weird. If we increase resistance, how much current's going to go through that resistor? Well, less. And if that current's not going through the resistor, where's it going to go? Into the capacitors and the inductors. And what are they going to do? They're going to trade energy back and forth, which is effectively what happens when things are underdamped. The more underdamped this is, the higher the peak as these guys trade energy back and forth. And so ultimately we reach the point where if we make this open, what is the voltage across these? We saw the series situation. If this is an open circuit, what's the voltage here? Well, it's kind of a tricky-ish question. If this is an open circuit and we're at resonance, what's the admittance here? If you're at resonance, what's true about ZL and ZC? Equal and opposite, they're complex conjugates. So what's the admittance if they're complex conjugates? Zero. So what's the impedance? If the admittance is zero, what's the impedance? And if we have infinite impedance and we're driving a current through it, what's the voltage? It's kind of a trick question, but what's something times infinity? Ohm's law still applies. You have infinite voltage, right? All right, not something we can really do. But we saw the similar situation when we looked at the series RLC circuit. If that resistance is zero, and we're at resonance, what was the current in the circuit? Infinite. Which, for some reason, it's easier to buy into an infinite current than it is to buy an infinite voltage. But it's the same argument. So, as this goes up, under damping, we drive more and more voltage. These guys trade energy back and forth, more and more energy back and forth. So that's what under damping is. As we're more under damped, these guys trade more and more energy back and forth. It's kind of an interesting phenomenon. It's real. Part D was missing some commentary. If there's a point that's greater than 0 dB, the damping ratio is less than 1. Is that true? Well, I left off an important comment here. It is true if there's no gain. And so that question wasn't right here. Everybody got that one. So if there's no gain, and you have greater than 0 dB, the damping ratio has to be less than 1. And we can also say it's not a bandpass filter. Some plot interpretations. People did generally fairly well on this. Phasor form of the source. What's the phasor form of the source? This one should be able to do like that. 10 angle 45. Everyone agrees? No problem. So there's the source, 10 angle 45. What's the approximate amplitude at 10 to the 6 of the output? I have not heard a right answer yet. Still have not heard a right answer. Finally heard the right answer. The source is 10 volt amplitude, right? What's the magnitude of the transfer function at 10 to the 6? So what's the output? 10, not 1. The transfer function is the ratio of the output to the input. Yes, a lot of times, like in the lab, we've been using a 1 volt reference source to make life easy. But it is still the ratio of the output to the input. So if our input is 10 volts, as is the case here, and we have a transfer function magnitude of 1 or 0 dB, then our output is 10 volts. The transfer function is the ratio of the output to the input. That's important. What about a 10 to the 5? Like 5. What's the roll off? Just a comment there. 20 dB. So what's the correction? At 10 to the 5, which is clearly a pole, minus 3 dB, which corresponds to what? Minus 3 dB is the transfer function equals half power, but we're talking about voltage. Not half voltage. Half power is correct. 1 over root 2. So 1 over root 2, 20 log of 1 over root 2 is minus 3 dB. And so at 10 to the 5th, the amplitude of the output voltage is 10 over square root of 2. Right? Then what about at 10 to the 2? That's not on the plot. Can we figure that out? Do we have enough information? Sure. Every 20 dB corresponds to a change of what in terms of the output over the input? Not half. 20 dB. Every 20 dB corresponds to 20 log of 1 is what? 0. 20 log of 10 is what? 20 log of 100 is what? So, a change of 20 dB corresponds to what? Change of 1 order of magnitude. So, effectively, what would 10 to the 2 be if we continued on our plot relative to the past band? Negative 60, which is how many changes of magnitude? So it's 1,000, 10 over 1,000, or 0.01, which maybe someone said didn't quite hear. What about the phase of the output voltage in 10 to the 5th? I want to make it a little bit more tricky, because you got to remember what the phase of the source was. 0. Phase of the source is 45 degrees. What's the phase? At 10 to the 5th, it's 45 degrees. And so what is the transfer function? The out over the in. I just said something was wrong. 90 degrees. So it's 90 degrees. Shift by 90 degrees. Onward. Everybody okay with this? Remember how to do the time domain expression? Omega's given. What's omega in this plot? Well, that's what we're talking about. Voltage source is defined as this phasor problem. I really don't want to do this one by hand. Is everybody comfortable with this? I could set it up if anybody feels a need. Certainly can't do it off the top of my head. Is everybody okay with phasors? I can historically say phasors are the more missed questions rather than the Bodie plots. People had a harder time with the phasor stuff than the Bodie plot stuff. Having an equivalent problem? No problem. What does this look like? How do you do this problem? Do we have any zeros? Sure. Where's our 0? It's 0. So we have a 0, 0. Do we have any poles? We have 3. 10 to the 2. And then 10 to the 5. 10 to the 5 is what type of pole? Double pole. So what does our Bodie plot look like? If I kind of cheat a little bit, just do it on paper. What's my slope? S less than 10 to the 2. 10 to the 2 less than S less than 10 to the 5. 10 to the 5 less than S. What's my slope for S less than 10 to the 2?
20.
Plus 20. So there's plus 20. What does my slope become as I cross 10 to the 2? 0. And my slope now becomes minus 40. Minus 40 dB per decade, plus 20 dB per decade, or if you prefer, you can just use roll-off. And then, for a reference, in the pass band, what's my dB? In the flat portion, what is my dB? I like 0. Why? Keep the dominant term. This is S, S plus 10 to the 5th squared, S plus 10 to the 2. Between 10 to the 2 and 10 to the 5th, what's the dominant term here? S, and what's the dominant term here? 10 to the 5 squared, or 10 to the 10. And so what do we have? 10 to the 10 times S over S times 10 to the 10, which hopefully we all agree is 1. We didn't write that out, but everybody see it? And comparably to phase. What's our phase? Well, for S much less than 10 to the 2, what's our phase? This is again something you should be able to do by inspection. 90. Does everybody agree? 90? And then what's the phase change as we cross 10 to the 2? 90 degrees over 2 decades. So what does our phase wind up looking like? We start off at 90. There's 10 to the 2. We change over 2 decades. That's 0. We get over 10 to the 5th. And what is our phase change here? 180. Beautiful. Minus 180. Not bad for not using Bowden's clock, I suppose. Everybody agree with that? Phase, again, phase is an area where more problems that occur. This wound up being, I think, quite an easy problem. First order low pass filter with 10 to the 2 as a cutoff. Well, it's a color. First order low pass filter with 10 to the 4. What's the transfer function? What's that? What's the numerator? Give it a 6.
I think so. It makes sense because voltage almost the same.
What's this? H1 of S equals 10 to the 2 over S plus 10 to the 2. You should be able to do that by inspection again. Low pass filter, first order, omega C over S plus omega C. That's worth going on the crib sheet. High pass filter, first order, S over S plus omega C. Yeah.
Is a unity gain the same thing as voltage fall?
Yeah, it's going to be gain out front, sure. H2 of S equals 1. H3 of S is 10 to the 4, but as opposed to. All right. And the last problem is another design problem similar to what you just did on the homeworks in the lab yesterday, etc. Okay. You owe me a minute and a half. Any questions?